So our first speaker this afternoon is Pavel.
Right, thank you. So let's just continue where we stopped last time. So I wanted to explain how to start with the differential algebra of differential forms on the manifold. Well, I'll answer it with the algebra of coefficients. And I wanted to go to the differential, to the cochain for triangulation. So T is a triangulation of my manifold. So I want to somehow construct the IPK triple or SDR data or whatever name you prefer for it, the inclusion, the projection, and the chain homotopy. So how to construct all that. So so actually it turns out that you can do it sort of simplex by simplex. So you can like take a standard n-dimensional simplex, and I explained, I wrote a formula how to, starting with a face of the simplex, one of the faces, to assign to it some kind of differential form, which is actually linear in barycentric coordinates, a differential form which has the degree the same as the dimension of the face. And it's called the Whitney denominative form, and I've written a formula for it. The formula is not so important, but it has some wonderful properties. And in particular, I have the following. That, let me maybe explain. Well, okay, let me explain it on the level of a triangulated manifold. So first of all, I have an easy projection. So this is a complex with the Ram differential. This is a complex with cell coboundary operator. Let me also write this. So the projection map is just the following. I take a differential form, and well, projecting it, I will obtain a sum over all simplices of my triangulation, all simplices of triangulation of different dimensions. Well, actually, only some dimensions will be relevant here. Simplices of triangulation. Then I should take the basis cochain associated to that simplex. Let me denote it E sub sigma. So basis cochain times a number, and the number is the integral of alpha over that simplex. So well, yeah, my simplices should be oriented. I just randomly choose orientations of simplices to make sense of that. And I understand that if I change the orientation, then this object changes sign and this object also changes sign. So, okay. Now that's the projection. It's sometimes called Poincare integration map. Poincare integration map. Now, the inclusion, that's where I want to use these elementary forms. So the inclusion goes like that. So I take, so essentially the inclusion just maps the basis cochain associated to a simplex to the corresponding elementary form. And you extend it by linearity. So once you extend it by linearity, you just say that you map a general cochain. Let's write it like that. You map it to the sum over simplices of well, the same coefficient times chi sigma. Where so okay, now what is this chi sigma? So now it's a differential form on the full on the manifold M. And well, it's if I consider some simplex which contains sigma as one of its sub-simplices, then the restriction of this form to this greater simplex is given by the formula that I wrote last time, given by Whitney formula. So let's say, I don't know, I have some triangulated manifold. Then sigma is this simplex. Then chi sigma would be a differential form on M, which sort of vanishes on each simplex which does not contain sigma as one of its subsimplices. But if I take some simplex which contains sigma as one of its faces, then the restriction of my form to here is given by this sort of linear in coordinates formula. So this full object is sort of piecewise linear. So this is a piecewise linear differential form with well-defined restrictions to every.
So are you saying it's not smooth though?
No, it's not smooth. It's not smooth. So actually, here I'm a little bit cheating when I'm saying that it goes to smooth differential form. So really, what should I really be putting here is sort of piecewise polynomial, let's say piecewise polynomial differential forms, which are allowed to break on the faces of triangulation, but such that their pullbacks to faces are well defined. So they can have different limits arriving from different simplices.
So do we have some special deformation track among piecewise linear?
Yeah, actually, those two objects they are.
I know they are
Well, there's a
quadratic. Yeah, but can we construct some special?
Yes, we can, but I don't want to bother with that. Yeah, but yes, we can. Yeah, possible. Yes. So for a relevant construction. No, okay. So I want to sort of give a reference to a sort of a related construction for how to construct such quadratomorphisms to the 2000 paper of Kancerich-Seibelman towards vibrations and topological mirror symmetry. So they needed like similar sort of how smoothing can be interpreted as a quasi-isomorphic, how to explicitly construct it.
Sorry, when you write an integral over a simplex, you integrate the pullback of the form, or you literally integrate over a closed subset?
Yeah, so I integrate the pullback of the form, pullback by the inclusion of that simplex. Right. So the simplex is included into M. I pull back and integrate. That's sort of implicit in the integral sign. Okay, so
Does Stokes' theorem still work for this?
come again?
Does Stokes' theorem still work if we have the forms breaking up?
Yes. Yes. Yeah, it works. So so for instance, maybe to have a feel for what kind of singularities are allowed here. So the image. So if I take, I don't know, like some maybe my M is a circle and it's kind of triangulated as some polygon, then well, I need to have kind of a pericentric coordinates on each simplex here. So for instance, zero forms would be some sort of piecewise linear functions, but with prescribed with sort of well-defined, so piecewise linear continuous functions. And so that would be in the image of I. But for one forms, it would be piecewise constant one forms. So that's what it would be. And those, so they would look like locally like some constant times dt, where t is the pericentric coordinate on the respective simplex. Okay. So now
to these one forms, you said they are of the form multiple of d theta.
Yeah.
At each point. And are you saying the multiples?
They could be different.
They could be different. So it's not even continuous at the level of one form. So
yeah, but the point is that the pull. So how do you test for continuity at the breaks? You pull back to that point, but since it's a one form, its pullback is zero.
okay.
So yeah, they're continuous in that sense. So the pullbacks agree, and well, they are a bit boring, those pullbacks. Yeah. Okay. So yes. So so the image of cochains here is sort of special piecewise linear differential forms. And well, it turns out, and this is kind of a wonderful property of Whitney's formula, it turns out that I is a chain map. It's not obvious. It is a chain map. Well, P is also a chain map, and that's a very easy statement. That's exactly Stokes' theorem. So P is also a chain map. Also, and that's also a property of Whitney's formula, if I compose P with I get the identity on cochains. That's in particular, that follows from certain properties of Whitney's formula. For instance, if I take this elementary form associated to a face of a simplex and restrict it back to that face, then I get the volume form on that face, which integrates to 1. And if I restrict to any other face, well, not contained in that face to which it was associated, then the restriction would be 0. So yeah, this kind of goes into that formula. Okay, so I think I explained part of the data, so the inclusion and projection. So now kind of the key part is the chain homotopy, and there is a nice choice here, which is due to Johannes Dupont. So I should say I learned this construction from a paper of Ezra Getzler about the theory for nilpotent and infinity algebra. So it's sort of for some completely different reasons, but sort of this data is explained there very nicely. So how is that constructed? So you have so let me construct it on a standard simplex. So you want to consider the following map. So you kind of build a cylinder on top of that simplex. And then you consider a homothety map. So I'll tell you what it means geometrically. So it's a map that takes a point in the simplex and some number from 0 to 1, let's call it u, and maps to the following. So I should scale all base-centric coordinates by u, but for the ith coordinate, I need to write 1 minus u plus uti. So I need to shift it by 1 minus, so that the whole thing still adds up to 1, and so on. Ut. So this looks like some bizarre formula, but its geometrical meaning is very simple. So you take your standard simplex and you fix the ith vertex, and this is a map which takes some generic point in your simplex and then pulls it towards the ith vertex, and sort of pulls it by a factor of u, so that when u is equal to 1, it doesn't do anything to the point. If u is equal to 0, it pulls it all the way to the vertex, right? So for u in between, it's for u1/2, it sort of pulls halfway.
So at the very end of the last line, what is after 1 minus u?
1 minus u plus u times ti. Plus u times ti. So essentially, I'm multiplying all coordinates but by u, but to preserve that the sum of the coordinates should be 1, I need to put this shift here for the ith coordinate. So yeah, so this is kind of elementary homothety or scaling map. And okay, so let me also consider the projection to the first factor here. Let's call it phi. So then what I want to consider is the following maps. So you probably have seen such diagrams, and you probably can imagine where it goes. So I want to take some differential form on the simplex. I want to pull it back by phi and push forward by pi. So I want to do this sort of push construction. So pi pull back and then push forward. Push forward is the same as phi by integral. So it goes from differential forms on a simplex to two differential forms 1 degree lower on the simplex, right? Because I have an integral over this one-dimensional fiber, so I'm integrating over this fiber, which drops the degree by 1. So these maps, they have also a good meaning. So this is a chain homotopy between identity on differential forms on the simplex and evaluation at the ith vertex. So okay. So then this Dupont's operator is constructed. So these are the building blocks of the Dupont's operator. So the Dupont's operator then is given as follows for the n simplex. I should be summing over I should be summing over dimensions. -1 to the k, -1 to the k, and then sum over k dimensional faces of my standard simplex. And then certain operator, and this operator is the kind of composition of these elementary chain homotopes. And then, so this sort of drops the degree of whatever I maximum, whatever differential form I maximum by k, because each of these drops by 1. Sorry, by k plus 1, because there's k plus 1 factor. And then I need to wedge it with the weakly form for that face, which sort of adds k to the degree. So the whole object has to be -1. So I drop the degree by k plus 1, and then increase it by k. So the whole object has degree -1. So the claim is that this is a chain homotopy operator. It satisfies all the properties. So moreover, so it has, okay, so let me maybe phrase it like that. So it's a theorem and different parts of it are due to different people. So it's Whitney, Dupont, and actually one very important property here was what proven by Getz was not known before. Namely, the fact that k squares to 0 was not proven before, and that was done by as well. So so what you have is the strong deformation retraction data from differential forms on the simplex to cochains on the simplex. So with inclusion by Whitney forms, with projection by the integration map over faces, and I think and the Dupont's operator. So so this is a collection of IPK triples or SDR data, whatever word you want to use. So if they satisfy all the axioms of IPK triples, and they are compatible with face maps with the inclusion of sub-simplexes into the simplex. So compatible face maps. And with the symmetry of the simplex, with Sn+1 symmetry, permuting the vertices of the simplex. Then, well, this compatibility with face maps ultimately means that I can glue a simplicial complex T out of standard simplices. So I can glue simplices and obtain an IPK triple. Well, obtain an IPK triple from differential forms. From differential forms on a manifold to cochains of a triangulation. Cochains of a triangulation. And again, I'm ignoring the distinction between smooth differential forms and piecewise polynomial. So yeah, so for example, well, if I have my triangulated manifold and I'm interested in how to construct the chain homotopy, then chain homotopy applied to some differential form on the manifold. So how it's defined? So it's defined by restrictions to simplices. So if I restrict it to some simplex, I should just consider Dupont's formula on that simplex and apply it to the restriction of alpha to that simplex. So that's it. And it turns out that this construction is compatible with restrictions to faces. Okay, so that's the kind of the induction data or IPK triple that goes into the page fixing corresponding fiber PV integral. So let me then tell you what this effective action looks like. The one induced on cochains of the triangulation. So now we want to play the kind of effective action game with V being differential forms on M. Now I want to tensor them with G. G is some finite dimensional Lie algebra. Some finite dimensional Lie algebra of coefficients. I can choose it to be anything. So this is a differential graded Lie algebra with one-time tensors with Lie algebra. So for my W, I want to choose cochain triangulation, also tensored to the Lie algebra. And the kind of the IPK triple is just the one over there, extended trivially by tensoring with identity to the algebra coefficient. So everything happens in the first factor. All these IPK maps, they are non-trivial only in the first factor. So well, fields of the theory of the effective theory at the level of W will be, well, the A field at the level of triangulation and B field at the level of triangulation. So A field is the sum over simplices sigma, the corresponding basis cochain times, well, it's a coefficient, and the coefficient here will be a Lie algebra element. So ultimately, it's a Lie algebra valued cochain, and the coefficient will have sort of intrinsic degree, and this degree or ghost number of that coefficient is equal to 1 minus the dimension of the simplex. So it's ultimately a G-valued cochain, and well, G-valued. And B is, well, a sum over sigma of the dual basis chains, E superscript sigma times coefficients. So the coefficients are in B star now, and they also have certain degrees. So the degrees are, what is it? It's -2 plus sigma. So, and this is a G star valued chain. So
What's the difference between the E lower index sigma versus subscript sigma?
yeah, there is a difference. So E lower index sigma is a basis cochain, and E superscript sigma is a basis chain. So I could also just write it as sigma, this basis chain. So okay, so the form. So then I should just repeat the computation that I was explaining last time with Feynman diagrams. Repeated with this IPK triple, but the fact that this IPK triple is essentially constructed by gluing together simplices results in a very nice sort of final form of the answer. So the form of the answer for the effective action is the following. So it's the sum, as at the level of triangulation, it's the sum over simplices of my triangulation of some kind of building block, let me call it S bar, for the simplex sigma, and it depends on the kind of components of the A field on sub-simplices of sigma. So A sigma collection of A sigma prime or sigma prime as sub-simplex of sigma. So and B on the top simplex here. Where does it go? Sorry, I guess the sigma prime is a superscript. Okay, yeah. So I'm kind of summing over simplices of triangulation of certain building blocks, and each building block depends on the kind of A's on sub simplices and on B on the sort of top cell. Also depends on H bar. So these are building blocks, local building blocks. And each building block, so essentially, each building block just depends on the dimension of sigma. doesn't depend on sort of the ambient geometry of triangulation and anything like that. So there's kind of a sequence of universal formulas enumerated by the dimension of sigma. So the formula for the sigma bar depends only on the dimension of sigma, dimension of the face, and well, restrictions of the fields to the two faces of sigma. So let me then tell you what these building blocks look like. Well, I can tell you something. I don't have sort of full explicit formulas for everything, but sort of they can be recovered algorithmically. But I can show you the first few answers. So building blocks. Building blocks as one. So for a zero-dimensional simplex, okay, zero-dimensional simplex is a point. The corresponding building block is, well, it's a point which has label 0. So then there's kind of field A0, Lie algebra valued field A0, and the cochain and the chain B sub 0, which is valued in G star. So this is the elementary building block for the zero simplex. So for the two-dimensional simplex, yes. So this formula might evoke various associations. If you stare at it, for instance, you could see that it looks like a Chevalier differential in the Lie algebra. So it's a Hamiltonian for the Chevalier differential. So okay, now for the one simplex, and that's kind of closely related to the formulas I started with yesterday morning. So for one simplex, the formula is like that. It's okay. So here I'm looking at an interval with endpoints called 0 and 1, and the bulk called 0, 1. So okay, so the formula is like that. And you should recognize some bits of what I was writing yesterday. So okay, so there is some kind of cubic term here, then plus some interesting function of adjoint of A01, which is an element in the Lie algebra. So there is the parabolic cotangent appearing here. So this is some expression in terms of A01. It's an operator, and I should act with this operator on A1 minus A0. Okay, so this is bracket with B01. And then the quantum correction minus IH bar trace over the Lie algebra logarithm of the CH adjoint A01 over 2 divided by the adjoint A01 over 2. These formulas appearing here, they exactly have to do with the Bernoulli numbers that appeared last time. So the expression written here, so it's some power series in the adjoint operator of A01. So it's a sum over k non-negative, the Bernoulli number B2k over 2k factorial, adjoint of A01 raised to the power 2k. So I take this adjoint and I add 2k times on the object that sits to the right, and then I pair with B01. So, well, let me call this function, it's some function f of adjoint A01. And this f is, well, it's a power series, it's 1 plus x squared over 12 minus x to the 4th over 720 plus da, 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 da. So there's kind of some funny function sitting here.
So what is the lambda 01? What's
A
there?
Sorry, A01. So that's this component of this discrete field corresponding to the, so it's a sigma, for sigma being the top cell of this interval.
I only saw a lambda there. Okay.
Sorry, it's A. It was supposed to be A. Apologies. Yeah. Okay. And Now, the formula appearing here, you might also have seen this formula. Maybe you have seen the determinant of this expression and some kind of Lie algebra object here. So you might have seen this formula if you know something about Lie theory and the exponential map from the Lie algebra to the Lie group. Namely, if you take the Haar measure on the group and pull it back by the exponential map and compare how different it is from the Lebesgue sort of measure on the Lie algebra. So they differ by a factor, and that's the factor, or rather that's the logarithm of the factor. So it's what's written here is a very initial object in Lie theory. So yeah, anyways, but you can also recognize Bernoulli numbers here if you like. So this logarithm, it's some kind of function g of adjoint of A01, and this function is also some power series with Bernoulli numbers in it, x squared over 2 times 12 minus x to the 4th over 4 times 720 plus da, 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 da. So Bernoulli numbers. Okay, so that's kind of the and you see the objects that appeared in this infinity algebra of the int. Now, the higher synthesis. Well, I cannot write down a closed formula for you, but I'll sort of try to say something about the building block for a high dimensional simplex. So for a simplex delta n, so let me use capital N here. So for a standard simplex, okay, so first of all, where does this object live? So it's a function on the space of fields associated to the standard triangulation of the standard simplex. And it's also a polynomial, actually a linear function in H bar. So the shape of the ansatz, let me write down the ansatz. So it's a sum over binary rooted trees gamma 0 with at least, well, with n leaves. Then the sum over subsimplices, n tuple of subsimplices of the simplex delta n decorating. So I'm thinking of this subsimplices as decorating the leaves of my tree, and the root of the tree will be decorated by the big simplex delta n. So subsimplices decorating the leaves. So decorating subsimplices, simplices decorating the leaves of the tree. Okay, so now the contribution of a graph and decoration would be, well, one of the number of automorphisms of the tree, then some rational number, some kind of structure constant, depending on the graph and the combinatorics of this n tuple of faces, sigma 1 dot sigma n. So that's some rational number, and then an expression in terms of the field components. So B field on the top cell, which is just an element of G star of the dual of the algebra, and then an iterated commutator, iterated Lie bracket of the components of the A field. So A sigma 1 dot A sigma n. So this is a collection of elements of the Lie algebra. Then I perform the iterated commutator or nested commutator prescribed by the combinatorics of the tree, right? So I just put the inputs on the tree, on the leaves of the tree, and then I sort of at each vertex I perform the commutator. So and then I read off what comes out at the root. That will be some kind of nested commutator. Then I pair it with B field. So it's what's called Jacobi graph, but actually a tree Jacobi graph. So it's nested commutator. Okay, so that's some kind of very natural expression in terms of the Lie algebra. And then kind of that was the tree part and the one loop correction. So that's minus IH bar, sum over one loop graphs. Connected one loop graphs, gamma 1. So with at least two leaves. And then a similar kind of structure, so sum over subsimplices decorating the leaves of the graph, one over the number of automorphisms, some structure constant, also rational number, and then well, the corresponding Jacobi. Well, okay, let me cut the loop at some point that will give me a tree. And the corresponding Jacobi sort of nested commutator, I think of it as an endomorphism of the Lie algebra. And then I take its trace over the Lie algebra. So so this is gamma 1 cut. So I cut the loop at some arbitrary place. I'll show no, didn't plan to show an example, but for instance, I don't know, like if gamma 1 is this graph, then I cut the loop someplace, and there's like a simple sigma 1, sigma 2. So then the expression would be, let's say, traversing this direction. So I take bracket of a sigma 2 with dot. Then I take the bracket with a sigma 1. That's a nested commutator, so I return here and I take the trace. Or maybe I should say super trace. No, it's just an ordinary algebra, sorry, it's a usual trace. So that would be the corresponding expression here. So the whole sort of non-trivial part is hidden now in these rational numbers that appear here, the structure constants. So computing them is kind of, it's an algorithmic problem. It's kind of non-trivial, but let me show you first examples. Structure constants. So let me show you the first few examples. So
Pavel, maybe you already said this, but why is it totally obvious that they're rational?
no, it's not. It's not. Well, for these ones, you can argue why this is so, and for these ones, I'm sort of cheating a little bit. There's a way to recover these constants from these constants by using quantum master equation, and then they will be automatically rational. But the ones that you would obtain by actually doing some sort of regularized super traces, they might fail to be rational, but then you know that you would be able to homotop them to rational values. So yeah, so I'm sort of referring to the particular way of recovering these constants.
Sorry, if we only have the tree level diagrams, you claim that we can recover the loop diagram
Yes.
uniquely?
Unique, good question. Well, uniquely up to an exact kind of a Q exact term.
Okay.
Yes. So essentially uniquely.
Okay.
See, essentially uniquely, yes. Okay. These constants don't depend on the algebra, they're completely universal. All the algebra data is factored out in this part. So let me show you kind of the simplest structure constants. Maybe show it there. Well, first of all, there's this simplest, very degenerate tree, which somehow corresponds to the term in the effective action corresponding to the cellular boundary operator. So, well, just kind of this tree. So, so this is the root, and the root I put the standard simplex, and here I put some subspace or some subsimplex of that simplex. Then the corresponding structure constant. Let me just draw it like that. C of that picture. So that would be, well, plus minus 1 or 0, and it's plus minus 1 if sigma is actually a codimension 1 phase of the simplex. If sigma is a phase of codimension 1. And plus or minus 1 depends on the orientation of sigma, whether it agrees with delta n or not. And 0 otherwise, if it's a higher dimension phase. Now, okay, now maybe more interesting example, if I have this tree. So I put delta n in the root, and then I put two faces here. So actually, if you ask me how, well, before I give you the answer, how to calculate this number. So essentially, this is the following computation. I take two faces of the standard simplex. I take the Whitney form corresponding to one face, wedge it with the Whitney form corresponding to the other face, and integrate. That will be some number. It turns out it will be a rational number, and it is okay. It's plus or minus dimension of sigma 1 factorial, dimension of sigma 2 factorial, divided by n plus 1 factorial. If, well, under some combinatorial assumption on this tuple of faces, namely, I want the dimensions of the faces to add up to n, and I want them to intersect over a point, and nothing more than a point. So I mean one of the vertices. So for instance, it could be like these two one-dimensional faces in a two simplex, and otherwise it would be zero. This is okay. This is a computation which is not very complicated, and the computations become more complicated if you have internal edges, because then actually you need to start using the Dupont's chain homotopy, and but these computations can still be performed. So here is the simplest example with an internal edge. And the answer here is, well, okay, again, depending on the combinatorics of the triple of subsimplices of a simplex, it's either something or zero. And this something has this combinatorial flavor again. Write down this formula times n plus 2 factorial, plus minus that or zero. And well, here's this or this depends on the combinatorics of the intersection of. Please let me try to draw the picture. So if points correspond to the vertices of a simplex, so let's say that this is sigma 1, this should be sigma 2, and sigma 3 should be. So this vertex 1 more vertex here, and a collection of some extra. Oops. Okay, I'm in trouble now. Yes, collecting an extra vertex here. So if this is the combinatorics of this triple of faces, then you get this formula. Otherwise, you get zero.
Sorry, Pavel.
Yes.
You lost me there with that. What is the condition?
Okay, so there is okay. There's a condition that's two faces here, so that there's the vertices, the sets of, so each simplex is a convex hull of a collection of vertices. Yeah. So that there's one common vertex between sigma 1 and sigma 2.
Right.
Okay. Yeah. So sorry, this is kind of the schematics of combinatorics of a triple of subsimplices. So now let me show you one example of loop graph. So honestly, computing the values of loop graphs is extremely complicated, because it's a different level of difficulty than tree diagrams, because you need to calculate regularized supertraces over the infinite dimensional space. So you need to, yeah, it's more complicated. But as I mentioned, there is a way to cheat. And namely, one can actually recover those values from the quantum mass equation from the standard simplex, from the classical operations. So, and well, in any case, the answer here is 1 over n plus 1. So here, this happens on simplex delta n. So here the answer is some funny rational function of the dimension of the simplex. So again, under some combinatorial condition, and here the combinatorial condition is very simple. So you need both simplices to be edges, and moreover, it has to be the same edge, and zero otherwise. So some kind of funny numbers. So yeah, but sort of if you have a lot of stamina, you can compute more numbers. So Yeah, so maybe one more remark that, yeah, so in these formulas, so there's this kind of complete formula in one-dimensional case, and that formula corresponds to the fact that one can calculate. So the contributing diagrams here are only of two types. So kind of this branch trees that have this very regular kind of pattern where you put like E0 or E1 here, and then E01 on all the other leaves. So that means, for instance, well, let's say you take E1, that means that you take T, wedge it with DT, then apply the chain homotopy, wedge it with DT, apply chain homotopy, and then you continue. And well, when you look at the expressions that appear here, the expressions will be Bernoulli polynomials in the coordinate on the simplex, and then in the end you have to integrate that Bernoulli polynomial and you obtain the Bernoulli number. So that's ultimately why the corresponding why Bernoulli numbers appear here. So why the structure constants are Bernoulli numbers. And in the quantum part, you're looking at the contributing graphs are wheel graphs. So this corresponds to calculating a certain super trace, infinite dimensional super trace. And actually, in this example, it's not a very complicated super trace over the space of differential forms. In an interval, you can use various regularizations, and whichever regularization you use, you will obtain the Bernoulli number. But it's an interesting computation. So, okay. Now let me maybe sort of, yeah, like said it already a couple of times, but just a little comment about these super traces. So, so on standard simplex, well, when computing the values of loop diagrams, you need to calculate the super trace over the space of differential forms on a simplex, and this needs a regularization. And then there are different ideas, different choices that one can make here. So there's one way which is an honest regularization, which actually works and sort of gives you answers, and that's how somehow originally this was computed. You sort of you regularize the chain homotopy operator. So you replace the Dupont's operator K with some regularized version, and this regularization corresponds to, okay, in the construction, there was this variable u that was the vertical coordinate along the cylinder. Is it still written here? No, not anymore. But there was kind of a simplex. Well, it was the kind of factor in this homotopy maps. So u was running from 0 to 1, and kind of k was involving the integral over its v. And in the regularized version, you just allow u to run from 0 to 1 minus epsilon. So somehow you say that a point cannot stay where it was. It has to go at least epsilon towards the respective vertex in those elementary homotopy maps. Turns out that if you do that, then all the values of Feynman diagrams are regularized. And in fact, something funny happens with that regularization, that usually when you regularize a Feynman diagram and try to remove the regulator, then it somehow explodes. Then you need to, I don't know, do some counter terms to make it finite. But here it turns out that the limit is just finite. Surprisingly, you don't need any renormalization, no counter terms needed. That's one of the ways to do regularization. There are other ways. Way 2 is cheating, as I explained. So the fact that cheating is possible is related to the fact that you are doing it on the standard simplex, and there you can prove that sort of solving the quantum master equation, knowing the classical part, is unobstructed. So one can recover the one loop part of the building block from the P part of the building block and the quantum master equation. And on the simplex, it's unabstracted, and the solution is unique up to a Q exact term. Okay, so those are the two ways I wanted to mention. But one can expand on the way one. But it's sort of, yeah. So you can solve this problem on a simplex, and then you put together the simplices. Okay, now kind of what's the big picture of what is happening here? So I have some manifold and a BF theory there. So kind of the continuum BF theory, where the space of fields is modeled on differential forms on M. Then, I can obtain by the fiber BV integral by constructing the BV effective action. I can obtain, if I have a triangulated manifold, I can obtain kind of an action on the space of field associated to cell cochains. So, and this is some sort of infinite dimensional BV integral happening here. That's why I'm drawing the dashed arrow. Infinite dimensional BV integral, but somehow it's kind of local in simplices. So you're doing some kind of computation that requires a regularization, which is exactly this regularization talking about here. But it's sort of universal in each simplex, and then everything is assembled out of those universal computations. Now, from that place, I can also go to a smaller place. From cochains, I can go, for instance, to cohomology of M. So then I can construct a BF theory on homology of M, well, with coefficients in the Lie algebra. So I can construct effective theory there. So this will correspond to some quantum L-infinity algebra structure on this space. And from this quantum L-infinity algebra, you can read off certain topological invariants. Some topological data about the space. And this is a finite dimensional. I can also consider different triangulations. For instance, I can consider some kind of subdivision of that triangulation. And then, well, on the one hand, I could have arrived here by this sort of standard infinite dimensional BV integral. You can also then go here by finite dimensional BV integral by sort of integrating out the redundant fields here corresponding to this sort of new subsimplices corresponding to the subdivision.
Sure.
Yes.
But this construction essentially depends on the smooth structure of the manifold. So all topological invariants are limited limits.
It doesn't seem that it's actually dependent on the smooth structure.
No, but the triangulations should be compatible with the smooth structure. Otherwise, you can't pull back forms or do anything.
No, sure. Yes.
Just
So
what kind of topology, like what kind of topology it depends on? Maybe is that what you're asking?
Well, I'm saying that topological invariants obtained this way seem to be limited to ones which are on the smooth structure.
So, well, no, actually, I don't think it depends on the smooth structure. So, and well, that's related to this comment that I'm a bit cavalier with the type of differential forms here that I could have taken piecewise polynomial differential forms. So I don't. I think it's not dependent on the smooth structure. And actually, I can tell you something about the invariants that appear here. But okay, so let me just finish this thought that I can sort of go in different ways. So I can go from a more dense triangulation to a more sparse triangulation, and then I can jump from any of those to the level of cohomology and obtain some kind of BF infinity theory there, which is equivalent to having a quantum infinity structure on the level of cohomology. So yeah, and I would be obtaining in principle different QL infinity structures, but they would be related necessarily by canonical transformation. So they would be, or quasi-isomorphic algebras, they would be in appropriate sense. So, okay, so somehow this picture, if you cut off all the dashed arrows, it is some sort of a discrete field theory. So you have gotten rid completely of kind of ill-defined infinite dimensional integrals. What's left is well-defined finite dimensional VV integrals, and sort of when you push forward to the lowest possible place, then you can read off some topological invariants. So what kind of topological invariants? Well, there will be a quantum L-infinity structure. Its classical part, classical L-infinity structure is okay. So I will obtain some kind of action at the level of homology. So it's a generating function for the quantum L-infinity structure on for chains of M with coefficients in the algebra. So the classical L-infinity operations, Lm at the level of homology, they are the Massili operations, the Massili brackets. And well, okay, so maybe there are people in the audience who know this better than me, but at least for a simply connected manifold, they encode completely the rational homotopy type. So they remember the rational homotopy type if the manifold is simply connected. But then there are also quantum operations, and they remember something more. So they are kind of a stronger invariant. So how stronger? So well, it's supposed to be something. Well, they're supposed to be interesting for a non-simply connected manifold, and they are supposed to be related to the Reidemeister-Raysinger torsion and its behavior in the neighborhood of zero on the modular space of flat connections. Stronger invariant. Let me maybe give you one example.
They are not homotopy invariants.
Sorry?
They are not homotopy invariants.
They are supposed to be a simple homotopy invariant, but there could be subtleties here. So maybe to recover the actual simple homotopy type, you need to start twisting the construction by non-trivial local systems.
And if you do that, then you don't have to worry about simple connectors anymore. You're seeing sort of all the possible.
I certainly want to allow non-simply connected manifolds for sure. So I wanted just to give you one example. So, and this example, it's an explicit computation, but it sort of involves some slight extension of the story where I could have repeated the story with replacing simplices by something a little bit more general. So I can actually do the story for cubical complexes or prismatic complexes. So you can actually write down the corresponding analog of the sort of IPK triple that I wrote. And the right side of the computation that I wanted to write here was actually using some kind of cubic complex. So if I take a circle and a Klein bottle, so their homology with coefficients in reals, let's say that there are homologies, isomorphic, and the sort of as the sort of infinity algebra structure, classical infinity algebra structure on homology is the same, so isomorphic. So there's just in one of the so essentially there's just the cut product and nothing else, no higher operations. Although this statement sort of is not invariant on isomorphism, so they should be saying it a bit more carefully. But there is a representative where there are no higher operations, just the cut product, which corresponds to this term in the effective action on the on homology. But there is also the quantum part, and the quantum part is different. So there is kind of a familiar formula. So A1 corresponds to the sort of the one cohomology of the circle, degree one cohomology. So this is the answer for a circle, and for the Klein bottle, there's something quite different here. Some different function. which corresponds to the fact that if I expand it in if I read optimal monomials in A1, I will see different coefficients. So it means that the quantum operations are different here. So from this algebraic structure of cohomology, so cohomology is isomorphic, cohomology with coefficients in reals. The classical operations are the same, quantum operations are different. So these two manifolds are distinguished by quantum operations. So, and well, okay, I'm out of time, so let me stop here. I will be talking about a completely different story tomorrow. So it will be a change of tune. Thank you.
Any questions?
All right. I think there's two different ways to define analytic topology. One is combinatorial,
Yes.
and the other is analytical.
Yes.
And you mentioned that to compute the one loop part of effective action functional, we have two ways. One is computing the Feynman diagram, and the other is solving quantum mathematics. Right?
Yes. Yes.
Can we give some proof of the equivalence of the analytic solution using this way?
So that was sort of like part of a dream here. Yes, to give it to. I'm not quite sure how it's related. Or maybe it's related to the question, but yeah, yes, you're referring to Jigger-Müller theorem, the famous theorem that Scheidemeyer torsion is equal to the Ray-Singer torsion.
Yeah.
That was kind of part of the dream here is to give another proof of Jigger-Müller theorem. I still don't quite know how to do it, but maybe it can be done. Yes, please.
On this like simple ones or I think like Chern-Simon's theory is used to distinguish small structures, right?
No,
Not at all.
well, in 3 dimensions there's Hauptvermutung.
Right. No, okay, never mind. So again, no, I can ask you later.
No, this question becomes relevant from 4 dimensions on.
Does your discrete version of BF theory really need to come from triangulating a manifold? Or
No.
it works with some more
No,
general
actually,
simple-
no. You can just assign it to a simplicial complex. Actually, yes. There's kind of I don't use Poincare duality here. Yeah. No. Yeah. Thank you for the question.
I guess follow-up question: is there like a cellular version of the story?
Yes, there is. But okay, there is a cellular version of the story. But I cannot quite do it in quite the same way by sort of pushing forward from differential forms, essentially because I don't know what would be the counterpart of Dupont's operator and of Whitney elementary forms. Those seem to be a bit subtle, and they cannot do it for a generic cell, like a generic boundary. But there's a different approach how to write down a solution of quantum mass equation in sort of this local way, and it's sort of interesting in its own right. I didn't have time to explain it, but it's sort of the idea is that you're sort of building your cell complex by joining cells of higher and higher dimension or non-decreasing dimension, and each time you're joining a new cell, you're sort of extending your solution of quantum mass equation by some new terms which involve the fields of the newly adjoined cell. So there is some sort of first bit that you need to add there, which corresponds to the cell coboundary operator, but that fails to satisfy the mass equation. And then it becomes a homological kind of abstraction problem. So you need to add higher and higher terms so as to kill the error term. And it turns out that it's possible, abstractions vanish, you can do that.
I guess maybe is it easier for like handle body decompositions, like somewhere between?
That I don't know.
Not a totally off the wall question, but can you deal with defects in BF theory this way? If I can develop a simplicial complex, can I impose some conditions on the fields or couple it to another maybe BF theory on that sub-complex?
Right. That's a very initial question, and I think there are sort of, well, yes, one should be able to put defects or observables, and sort of there are easy things to put in and hard things to put in. Essentially, the hard things are the ones that are of higher degree in the field B. So if putting in something that's at most linear in the B field, so then it's easy, some kind of observable. And yes, so if you put in something of high degree in the B field, then as far as I remember, sort of you start breaking the simplicial locality property of the answer. It starts sort of spreading around in the triangulation.
this, as long as it looks sort of still kind of cotangent or something in the B direction or.
Yeah, yeah, then, yeah.
Okay.
Yes, then it sort of, it preserves the locality property. So I don't know, mysteriously or not, but this linearity in B is also the same as condition in geometric quantization. So, yeah.
Well, if there are no further
I
questions.
think that's
let's-
quite.
I'm so sorry.
How does the effective theory that you get from triangulation relate to the effective theory you get from triangulation?
Oh, the dual thing triangulation is not a triangulation. So it's a cell complex. Sometimes, very rarely, it is a triangulation. But generally, so yeah, that's a good question. There's actually a version of that story which deals with the cell version, which deals with the dual cell complex, and then actually then A becomes a cochain of a cell complex, and B becomes a kind of a cochain of the dual rather than chain of the original. So somehow what you are asking is, can I interchange A and B? And the answer is that very easily in abelian theory, and doesn't quite work in the non-abelian theory.
But if we do this for cubes, then we would get an absolutely dual thing, right?
Yes. But sort of still the roles of the A field and the B field are different. It's true that you can have like a cubical complex and its dual will be also a cubical complex sometimes. But still, sort of one of them will be distinguished between one of them will be carrying the non-trivial continuity algebra structure.
So sorry. I want to ask, what's the difficulty to run this program for Chern-Simons?
Oh, okay, good question. So there are as an intermediate. Okay, in Chern-Simons, the biggest one is putting Poincare duality on a triangulation or on a cell complex. That's kind of the big problem. But there is sort of an intermediate step where you don't need to put the Poincare duality in the game. That's something like BF plus B cube theory, for instance, which is sort of halfway towards Chern-Simons. BF plus B cube is a three-dimensional theory.
Okay.
It's kind of it's relevant in physics as three-dimensional gravity is cosmological term. So B cube is a cosmological term. But there you can try to play this game, but again you will have problem with taking the products of B field, which is, well, on one hand it's an analytical problem because somehow B field in this gauge fixing is somehow represented by delta forms on faces of simplices. So you need to resolve the products of currents. That's one analytical issue. The other is that, well, again, you will have something, at least not such a nice answer as a like sum over simplices. It will be more complicated. So simplices will be seeing more distant simplices. So that's kind of what I think. But I don't think that it's undoable. It's maybe just the answer is not as nice.
Any other questions?
So are there any issues with like gauge fixings?
No, I don't know. I love this gauge fixing that I explained to you. So I don't know what you mean issues. Well, some issues for sure. Like for instance, that it maps to not smooth forms, but piecewise polynomial forms, or that this dual IPK triple that you need for the B field somehow it maps kind of basis chains to delta forms on the chains. So there are some analytical issues, but I think, well, in this theory, you can work with them. If you add higher terms in B field, then there could be problems. So there are many different gauge fixings one can play with in BF theory. So this is just a story of one particular gauge fixing that plays well with the triangulation. There are other very nice gauge fixings, like the one that sort of works well with Morse theory. That's another very nice story. Yes, please.
Yeah, sorry. So you keep referring to this issue that we have piecewise forms, but if we do like differential cohomology, then this is sort of automatically taken care of, right? Or
I don't know.
we have like these correction terms.
I'm not quite sure what you mean. Maybe we should discuss separately.
Right, well, if there are no further questions, let's thank Pavel again. So our next talk is by Owen at 4 o'clock.
Yeah. Basically, this company has like